Okay, I should be live. Good morning, good morning, good morning. I hope everyone is here. I'm going to share everything on our classroom. I updated our OS, or my OS, excuse me, just in the hope that things would move a little bit quicker. Let's see what happens. Here, hi, this YouTube, whiteboard. Okay. Have that here. I hope someone is in here right now. I can't check at the moment. I will shortly. That's very crazy. Okay. Let's go. All right. Let's see who's here. One viewer. All right. Welcome, welcome. Welcome, welcome. Two viewers. Okay. Three viewers. All right. Just please reply good morning or something so that this way I know that. Oh, good morning, Dahlia. Thank you. Good morning. Good morning, everyone. We have five viewers more. Good morning, Karen. Good morning, Edgar. Okay, we'll just wait a few more seconds. Hey, Liana, how are you? Hello! It's a nice sunny day. I hope everyone had a great weekend. Good morning, Eleni. Good morning, Leah. So I don't know what the delay is, but there's viewers that are going in and out, it seems. Okay, so we're going to begin. We'll go to PowerPoint. And let's see where we last left off. We're still looking at inverses, I think. Right, right. So I'm just looking at my notes now. So we looked at some inverses. The notation, that's really what's important here, the notation. And what we're going to focus on today, again, there's some slight delay. Good morning, Elizabeth. All right, so our notation for today. So, or what we're going to be focusing on. We're going to be focusing on writing the equation for the inverse. So finding the equation of the inverse when we have some function f of x. So it's pretty simple. The board, let's see if the board's working. So we'll do our daily check of the board. Where are you? Here we go. I had it. Okay, good. All right. So let's see. We'll do our daily check. Just make sure that the link works. I'm going to write something here. I don't know. Let's see. Please confirm that it works. Good morning, Zayad. Valentina, good morning. Sydney, good morning. Sarah, good morning. Jocelyn, good morning. So many people. I'm glad to see you all here. So if the board's working, please just write whatever's on the board. Morning, Brittany. Good morning, Josh. So again, if you can just click on the whiteboard link. That's right. That's right. Sunny days today and ahead. Awesome. Great. So, see, it's great seeing the back and forth. See, positive message. All right, so very simple what we have to do today. We're going to write the equations of inverses and what we were talking about in the last class. So again, x, y, what we're looking at it becoming is really yx. And if you remember the transformation, so if you remember the transformation where you're switching y and x, do you remember? So we have options here, right? So I'm going to help you here. We have reflection, just to name a few. Let's see, translation. We have dilation. I'm going to abbreviate. And then lastly, rotation. Abbreviated, just because of the room space. So, of all of these, which one do you think we're going to be looking at? Is it a reflection, translation, dilation, or rotation? So in other words, when xy becomes yx, so now I'm asking you to think back to those geometry days. So here, which one, or what happens when we switch x and y? Is it a reflection, translation, dilation, or rotation? And it's okay if you don't remember, because we're going to spend some time looking at that. I have a feeling that it might be too early. I know it's Monday. So we're going to be looking at the following today. So everything that we're doing is related to this. Big old reflection. So if we look at the next slide, so you should have this. This is a continuation of where we last left off. So here, what we want to figure out, first of all, is the whole one-to-one, right? Decide whether each equation defines a one-to-one function. If so, then find the equation of the inverse. So we're still using the class notes from the last class. So everything has been updated. As we move along in today's lesson, we may be hitting on some of the new material that I've posted, but I'll keep you updated as we move along. But for now, we're continuing on where we last left off. So here, we could graph this y equals 2x plus 5. Again, it will be, we can perform the horizontal line test, and if we do that, it's going to clearly pass that test. So we'll have a one-to-one function. But more importantly now is this. So I'm going to write this now on the board. So you're going to follow along with me. The arrows are going down, so you will drag the screen. We're moving down. So now we're here. Hopefully you followed. And we're going to look at this. So f of x is going to equal to 2x plus 5. All right, but we're going to change that to y equals to 2x plus 5. Because again, f of x and y, they're interchangeable. They both relate to outputs. So what we're going to do, according to the inverse, all we need to do now is switch the placement of x and y. So I'm going now down here. So again, follow the arrows, dragging the screen down. And what we're going to do is we're going to change the location of y with x and the location of x with y. So what we're going to do is now essentially solve for y. So we have to get y alone. So we started with y equals 2x plus 5. But if we're going to look at the inverse, we're switching the location of the variables, and we're going to solve now for a new y. So in doing that, we must subtract 5 to both sides. So again, I'm moving the screen down. And we're left with this. X minus 5 equals to 2y. And to get y alone, we would just divide 2 to both sides. So I'll show that here. So if you look at the following, it's going to change in a second. There's a delay. It will change at some point, I'm hoping. Wow, the delay is so terrible. I'm just waiting for the slide to change on your end. So that's why there was that gap there, or that silence there. And I'm not sure why it's taking so long. Oh boy. All right, so if you're still looking at the board is up to date. The stream is a little bit behind. So if we change this, so again, I'm moving down, still moving down. We're going to have the following. We're going to have x minus 5 divided by 2 is equal to y. So now this is our new value for y. And the only thing that we have to change now, the only thing that needs to be changed is, oh, there it goes, it changed. And just so you know, it took almost a minute to change slides. So anyway, going back to the board. So instead of y, we're going to write that as f inverse. So following along, we're going to write that now as f inverse of x is going to equal to this, x minus 5 divided by 2. And you should be seeing that now in front of you. And if you look at the solution, the only thing that happened, and again, just following along down, the only thing that happened was that there was a splitting, or 2 was divided into both x and negative 5. So in other words, I will rewrite this so that it reflects or mirrors what you see. So this will be half x minus 5 divided by 2. That will equal to f inverse of x. So that will be the final answer here. So to write this, again, the equation of the inverse, all you're doing is you're changing the location of where x and y are and solving for a new y. So if we look at this example here, so we're going to move on to example 3, 3b. I hope that's what's in front of you now, 3b. So I'm moving along, and there might be a delay from when I tell you to slide down as to what you see on the whiteboard. So that should give you some idea as to the lag, and I'm so sorry that you have to deal with this, but at least we have a means to communicate. Positive thoughts. Sunny days. So moving down, we're going to look at example 3b. So 3b is x squared plus 2. So this is going to equal to f of x. So the first thing that we would do, we could do the horizontal line test. So that's number 1. But in an effort to save time, I will graph it here. This is so poor, my mistake, or not my mistake, my apologies. But it would look something like this. I know. I've become a great artist, working remotely now. Don't tell anyone. But anyway, so what's going to happen is this. If we do the horizontal line test, we're going to end up failing because it's going to hit these 2 points. So this is 1 to 1, or not 1 to 1, excuse me. So if it's not 1 to 1, it will not have an inverse per se. although we can write the equation of an inverse here, we could. And if you look here at the example, if you look here at the example, we could physically substitute or change out x and y, and we could solve for y. We can get it by itself. But even in doing that, this is not considered to be a one-to-one function. So if that's the case, it's not going to have an inverse. Although we could write the equation for it, by definition, it will not produce the inverse. And again, I wish I could show you graphically how this looks like, at least in a proper graph, but if you look at the whiteboard, you will see that it fails the horizontal line test. It's going to fail it. So if that's the case, it's not going to be one-to-one. And if it's not going to be one-to-one, then we cannot have an inverse for this function. Again, although we can write the equation of the inverse, we can do that. This is not going to be considered one-to-one. Although I'll do it here just so you can see. So it's a good practice in isolating y. So if you follow along. So we had what here? Y is equal to x squared plus 2. You can make this x is equal to y squared plus 2. And again, moving down, we can get y by itself. Again, we subtract 2. We take the square root of both sides. And again, moving down here, we would have plus or minus radical x minus 2 is equal to y. But again, if it's not one-to-one, then this function does not have an inverse. And it's just because of those, the signs, and how we're going to have both roots. So that's why it's going to be a little bit confusing, or it's going to result in not having an inverse. But if we look here, if we look at example C, so if we look at example C, so here we're moving down, and I'm going to stop here for 1 second. Wait, hold on, Mr. Hakan, how would you want us to explain if there were inverses or not? Thank you, Kyle. You could. So if you're asked to defend why you do not have an inverse, you could say that it would fail the horizontal line test. And then you could graph it out, and then you can see exactly where, for the x values that you choose, that you'll have identical y values. You could, definitely. And good morning, Melissa. So there is a huge lag. So I'm just curious, I'm just going to ask the class right now. Is it inconsistent when I'm using the whiteboard and what you're hearing from the YouTube live stream? So again, I'm asking you, as I write on the whiteboard, is the whiteboard faster than what's coming out of YouTube Live, like my voice? So again, my question. So as I'm writing on the whiteboard, is the whiteboard ahead of the work that's going on in YouTube Live? Or is the voice pretty much spot on with what's going on the whiteboard? Sometimes, but not by much. Okay, good. Thank you, Brittany. That's all I needed to hear. All right, so moving along. So if we look at example 3 now, so you have, and you're following along with me, we're following along. So here you have f of x That's going to equal to x minus 2 raised to the power of 3. But if you graph this, and I'm going to pass this, or I'm going to move on to the next slide, excuse me. And if we look at the graph, you'll see that it's going to pass the horizontal line test. That's number one. So it's going to have this one-to-one relationship. So if we have it, then we're able to write the inverse for, or at least state the inverse for that function. So in other words, what we're going to do is the following. We're going to, again, replace f of x with y, and then we're going to substitute in, or replace or switch x with y and y with x. So we have the following. So now we have to get rid of the cubic root. So to do that, we have to get rid of the cube, excuse me. So you have to take the cubic root of both sides. And if we do that, again, moving along, we will have the cubic root of x equals to y minus 2, but we would just add 2 to both sides. And again, following with the arrows. And I think you're able to zoom out. So if you zoom out, it's not going to look, the flow of everything will be a little bit better because it's going to be, one on top of the other and then just descending down. I'm just showing the arrows because I'm zoomed in 100%. That's basically it. And my space is limited. So moving down, if we look here, you will have the cubic root of x plus 2 equals to y. But don't forget, and this is the most important part, you must change y to f inverse. F inverse, that's proper notation, or it's going to look like f to the negative 1 power of x. That's going to equal to the cubic root of x plus 2. So this will be our final answer, and it should be projected or displayed on your side in about a second. So with regards to graphing, so if you know that the two functions are inverses, then what's going to appear is this symmetry. And this is going back to our conversation related to the transformations. So when x, y, so here I'm back to the board, I'm just going to go down a little bit. So when x, y, when we're told to switch y, x, that's going to represent this red line here. So the red line is a line of reflection, and that line is y equals x. So if we were to graph not only the given function, but its inverse, if we graph this line y equals x, we would see symmetry. That's number one. It's going to be symmetrical, but this is kind of going more into the geometry. It's going to act as a perpendicular line between 2 points. It's kind of going above and beyond what we need to cover. But just some important facts here about inverses. So if f is 1-to-1, then f inverse exists. So that's the whole thing. So if you have a 1-to-1 function, then you can write the inverse of that function. You can graph it, and you will clearly see the symmetry along this line y equals x. So number 2 here is important, very important. The domain of f is the range of f inverse, and the range of f is the domain of f inverse. So let me just read that again. So the domain of f is the range of f inverse, and the range of f is the domain of f inverse. So basically, x, y becomes y, x, or this switching. And number 3 is also important. They're all important. But 3 kind of goes along with what we were just saying. If point AB lies on the graph of F, then the inverse, or BA, lies on the graph of F inverse. The graphs of F and F inverse, are reflections of each other across the line y equals x. And number 4 basically goes into what we were just talking about. If you want to find F inverse, just change x and y and solve for a new y. So in looking here, I want to make the most of our time. Normally, I would give you time to practice. We would have 80 minutes. We don't have that luxury anymore, but we're making the best with what we have. And these would have been assigned. So I'll let you take a look at this for a second, just so you can see the types of questions and the phrasing of the question. And then in about 10 to 15 seconds, I'll give you the solutions. You can take a screenshot. You can take a picture. I really don't care, as long as you have it there for your records. And you can certainly practice independently. So take a look at this. This you should have. And then I'll give you the opportunity to take a picture of the solutions in a few. And in case you're wondering, I am still drinking coffee. It's in my hand. It's not Dunkin'. It's some like fancy schmancy coffee. I don't know. Califia? 100% Arabica coffee? I don't know. I'll share a picture of it later. I took one this morning. My new school is all about, saying good morning and sharing pictures of like coffee and stuff like that. I know, very exciting. So there are the solutions. So make sure that you take a picture. And we're going to move on to exponential functions now. So again, all the memes that I find, I don't create them. They exist in the internet. I have nothing to do with them. It's just whatever catches my eye. And this caught my eye. So in this section, we're going to be looking at exponential functions, some exponents and the properties, exponential equations, compound interest, the number e, continuous compounding, and we're going to be looking at some exponential models. So let's see what's happening here. I'm going to zoom in. When your barber knows the exponential growth and decay formula. Wow. I got to go to that barber. Actually, funny story. Not funny, but so I wanted to get a haircut before everything shut down. And my main barber, I hit him up through text, and he's like, I'm sorry, I cannot cut any hair, closed indefinitely. And then on the last day before barbershops closed, I had to run and find one because I needed to look fresh for no one, right? Anyway, so yeah, the moral of the story, go to a good barber, find a nice hair salon, and there we go. All right, so back to me, or back to this. So let's see, some properties that we've looked at. So I think we already did this, or we covered some basic properties of exponents. At some point, I want to say chapter 1. We looked at that. I'm so sorry. Okay. That's spam, and I'm hanging up on them right now. Don't tell anyone I do that. Anyway, so, all right. So let's look. Recall the definition of A, and then we have that raised to the power of m divided by n. So what we're able to do is the denominator of this fractional exponent. That becomes the root. And the numerator of this fractional exponent becomes what we're raising this entire base to. So as an example, if we have 16 raised to the power of 3/4, that's really the same thing as saying the cubing of the quartic root of 16. Blech. I know, it's a lot of stuff. It was said very mathematical, but it's basically saying this. So we raise something to the power of 3. What are we raising to the power of 3? The 4th root of 16. And don't forget, very important, the negative exponents. Negative exponents here, again, what that means is that the base is in the wrong place, for lack of better words. So if we have our base in the numerator, there's a negative exponent. It goes immediately to a denominator. And if it's just a value that's not fractional, then the numerator becomes 1. And again, we apply the same rules. The rule being here, if we have the fractional exponent, the denominator is the root, the numerator is what you're raising that whole thing to in terms of a power. Okay, so hopefully those examples were okay. Great. Moving along here. So this, I think, is all in your notes. Well, I think I gave this to you at some point when we were in brick and mortar world. So again, just some, and again here where it says you remember these rules, we just spend a lot of time going over the fractional exponent because that's going to be important in our conversations that are going to occur in these next few lessons. Okay. So here, just some properties again of exponents. So if we have this graph of f of x is equal to 2 to the power of x, so what's going to happen is that the more values that we plug in for x. So we can look at integers, right, of the exponent. So 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, etc. So that's going to give us those points. But then if we look at all values of x, so all real numbers of x, then we're going to be able to put more points along this graph. And then clearly what we're going to have is this line. So the line for an exponential function. Okay, so let's see, additional properties. There's a lot of properties here. So I want us to move to example 1. So take a moment to go into the classwork. It should be something labeled exponential functions and compound interest, I believe. I'm just going to get the title of it. Just give me 1 second. So this is where you're looking at the correct work. We should have here, I'm so sorry, where are you? Exponential functions, I think that's what it's called. Yeah, so the title of this handout is exponential functions. So when you're looking in your classwork tab, exponential functions. So let's look at this example. So it's saying here, if f of x equals 2 to the x power, we have to now evaluate. So this shouldn't be too difficult here. So if we evaluate this, so here's the whole thing. This is good practice with the negative exponent. So if we have 2 raised to the power of -1, as was mentioned before, all that means is that the base is in the wrong place, for lack of better words. So I'm going to show you here. We're going back to the board for 1 second. So again, follow the arrows. So following the arrows, so here we have f of -1 is equal to 2 to the -1 power. Think of it as 2 to the -1 power over 1. Think of it that way. So if the negative exponent bothers you, just think of it this way. Oh, I have something over 1, so that means that I have to put it in the denominator. That's what that means. But then my numerator becomes 1 because I was only dealing with a non-fractional value at this moment. So we have 1/2 raised, or 2 is still raised though to the power of 1. So you can't forget that although you have the negative exponent, that when you bring it to the denominator, that we make that exponent now positive. And clearly 2 to the first power is just 2. So here looking or moving along, I think these are painfully easy, but again, it's just, working with the actual exponential function and evaluating. So here we have f of 3. We plug that in for the exponent, 2 cubed. Clearly 2 cubed will equal to 8, so that's really not too difficult. But this is where I'm going to now test you slightly. So we're going back to the whiteboard, we're moving down, and now we have this. Now we have, this is example 1c. F of x is still equal to 2x, but now f is 5 divided by 2. So in other words, we have here, when f, we're evaluating that, we have 2 raised to the 5/2 power. So now this is where it becomes a little bit different. There's a few ways that we can do this, right? There's a few ways. So if you looked at the previous examples, right? Let me go back to a previous example here. So if we look here, we can do this one of a few ways. So we can immediately make the denominator of this fractional exponent, we can take the cubic or the x root immediately of that base that we're given and then raise it to a power. We could do that. Or we could play around with how we express that fractional exponent. And if you look here, going back to this example. So look at what we can do. So we could actually raise the base to the power of 5 first and then take the square root of it. Because now we're applying properties of numbers. So 5/2, and here we're writing here, 5/2 is really the same as 5 times 1/2. And if we do that when we're raising powers, so look at what happens here. So again, we're going down now on the whiteboard. So we have 5, or f of 5/2. So I could write 2 raised to the power of 5, but then, or let me rewrite this, excuse me. So 2 raised to the power of 5, but raise all of this to the 1/2 power. Because what ends up happening is that this is still the same as 2 raised to the power of 5/2. They're mathematically equivalent. So if we do it that way, either way, we're going to get the same answer. So if we do it that way, then we're going to be left with radical 32. But radical 32 will just simplify the 4 radical 2. So if you want me to do it the other way, and again, here we'll go to the whiteboard again, we're going down. So if you really wanted to adhere to what the rule is traditionally, then this would have become the square root of 2 raised to the power of 5. But if we write all of that out, so we did radical 2 times radical 2 times radical 2 times radical 2 times radical 2, all of that would be radical 32. And then if we simplify radical 32, then we still end up with the final answer of 4 radical 2. So in other words, there's some flexibility here. So the next set of examples are going to deal with graphs and the properties of the graphs of an exponential function. So being that we have a few more minutes left today, so if you look through your PowerPoint, it goes into more detail as to the range and the domain for exponential functions. So this is for the example of f of x is equal to 2 to the x power. You can see that the domain is all real numbers, but there's going to be a limit on the range. Similarly, if you look at now a fractional base, or a base that's in between 0 and 1, The domain will still be the same, or all real numbers, and the range, for the most part, will be somewhat similar as well. But it's just uh, how the graph appears. One would represent a growing, and the other one will represent a decrease, or in the language that's used within this world, a decay. So the next two examples are going to, or at least this one example that I see, it's going to involve graphing, and typically you would have graph paper to do that. I could share that with you, but what I'd like for us to do, or at least focus with the homework, I believe, so let me clarify. So what I want you to finish for tonight's homework is going to be the following. I'm going to extend the submission of what you were supposed to give me tonight, or today, excuse me, and then you can just do all of that on one submission and it will be due tomorrow. And this exponential function stuff here, I'm going to go in, I'm going to edit that, and then I'll give you a revised assignment. So it's not going to be too much. I think many of you already finished the handout that I gave, but if you didn't, then I'm going to extend the due date for that for tomorrow. And then I'll add some stuff with exponential functions. But for now, that's it. We went through a lot. I think I kept you 1 minute ahead. I apologize, but again, there's just some technical difficulties this morning. I wish you an amazing Monday. And if you have any questions, I'll be around. You can always message me, Jupyter, Google Classrooms, whatever it is, I'll be there for you. And that's it for today. Have a great day, and I'll see you tomorrow. No problem, Sarah. Have a great day, everyone.